So now we talk about the Legendre symbol, how to compute the symbol. There are several properties. I'm going to just put everything into a single statement. All these theorems in a single statement. So let's say we have this it has lots of different parts. Let's say 1. If I have a square, the Legendre symbol is 1. If, meaning p is a prime and it's a number that's not a multiple of p, it's any integer number. But if it is already a square, then the Legendre symbol is 1. So let me write p prime. Actually, p odd prime, we're not going to have any 2 in there. And a relatively prime with p. So now, a second property, and this is also clear. The first one is clear. If the number is already a square, of course it's congruent to a square. It's congruent to itself. So it's a quadratic residual. So the symbol has to be 1. Now, if I have two numbers that are congruent to each other, if one is a square, one is congruent to a square, and the other one is congruent to a square, the same square. So if I have two numbers, a and b, and if they are congruent, if a congruent to b, mod p, then the symbol is the same. Both are 1 or both are negative 1. Now, very nice property. The product, if I have the product of two numbers, the symbol is equal to the product of the two symbols. Maybe we can prove this later. But now I won't stop. I just want to write all these properties on the board, and then we start to work with them to see how we can compute any Legendre symbol if we have these properties. Anything else? Yes, there are two special cases. If one of the numbers is minus 1, if a was minus 1, and the symbol is minus 1 over p, it's just minus 1 over minus 1 to the p minus 1 over 2. And this means that if p is congruent to 1 mod 4, when you subtract 1, it's congruent to, so if p is a prime that's congruent to 1 modulo 4, like 5 or 13 or 17, subtract 1, divide by 2, it's still even and in the exponent. So minus 1 to that thing will be plus 1. But if p is congruent to 3 mod 4, like 3, 7, 11, 11 minus 1 is 10, divided by 2 is 5. It's an odd number in the exponent, so minus 1 to the 5 is minus 1. So in conclusion, this symbol is 1 when p is congruent to 1 mod 4, and it's minus 1 if p is congruent to minus 1 mod 4. I don't have to keep that in mind. I just remember the property if I can. There's another particular case. Let me put it here because then I need more space for. So that will be 5 actually. If I have this prime number 2, it's a bit more complicated. But we do have a formula in this case, and it's minus 1 to the p squared minus 1 over 8. Always. I would like to write it p squared minus 1, it's a difference of two squares, we can factor as p minus 1 times p plus 1. And this is how I like to see it written. It's minus 1 to the p minus 1 p plus 1 over 8. this is always an integer number, p being an odd prime. Because p is odd, p minus 1 is even, p plus 1 is even, and one of these two numbers is actually a multiple of 4. So the whole thing is a multiple of 8. It could be a multiple of 16 sometimes, and then you divide by 8, it is still even, and minus 1 to that thing is plus, or plus 1. Or it could be that the number there, it's just a multiple of 8, but not a multiple of 16. When you divide by 8, you get something that's odd in the exponent, so minus 1 to that odd number is going to be minus 1. But it's always equal to those. And the last one is the so-called quadratic reciprocity law or theorem. It was conjectured earlier, Gauss proved it. And maybe has different formulations that are equivalent to each other. The way we use it is when I need to compute a symbol. So I write it in this form. Suppose I want to compute this. Say, when Q is also a prime. So here P and Q are both primes. So the assumption is that P, Q are all primes. P was an odd prime from the beginning, but Q could be an even number that's a prime. But the only even number that's a prime number is 2. And for that we have another formula right here. So the remaining case is when the prime number is odd. And when I have this both numbers odd, and this is, sometimes it's equal to this other quadratic symbol. P over Q symbol. And sometimes is equal to minus this one. So QP, PQ. Sometimes we have a minus in front, in the sense that one of them was 1, the other is equal to minus 1, and sometimes they are equal. And this quadratic reciprocity tells us when we have, exactly, it tells us when we have a minus in front. And we have a minus in front if and only if, so only in these cases, if and only if both numbers, P and Q, are congruent to 3 mod 4. So this happens if both of them are congruent to 3. So if P congruent to 3 and Q congruent to 3, mod 4. Now if at least one of them is not congruent to 3 mod 4, in which case it's congruent to 1 mod 4. So if at least one of them, if at least one of our primes, P, Q, at least one of them, P or Q, is congruent to 1, say, mod 4, then I don't have a minus in front. The two symbols are equal. I don't know if we can maybe move this laptop a bit, just so I have some space here. I will need. If it's not needed, it's fine. But I want to have all these properties on the board when I show an example how to compute it. Maybe just rotate all of it.
That's what happened yesterday. It can break, so I don't want to risk it. Let's keep it like that.
Oh, okay.
This much is fine.
Yeah, if I have enough space here, okay, no problem.
You have this much.
Okay, that's enough. Let's see. Ask this question. I think I had a question before. Is 73 quadratic raised to mod 37? So in that case, I compute the symbol. So we say is 73 a quadratic residue mod 37? Question mark. And we said that we'll do it just by computing. So I compute, or we say we compute the symbol 73 over 37 equals. I can use any of these properties that I want. I cannot use the first one at this moment because 73 is not a square as an integer. I can use the second one saying that I can replace 73 by any number that's congruent to 73 mod 37. So I can, for instance, write what's 73 minus 37? It's maybe 36. I mean, from 73 I can subtract 37 or a multiple of 37, or I can add a 37. I always get numbers that are congruent to the given number, 73 mod 37. If I subtract a 37, I think I get 36, yes. 36 plus 37 is 73. And once I do that, this is not 1 directly from the first. Because 36 is a square. That was too easy. I'll do another one, because I want to see how we use quadratic reciprocity. Oh, by the way, I cannot use this on multiplicativity. Because 73 was a prime number. I'll write it as a product. But I can use quadratic reciprocity. So if I don't see the fact that 73 minus 37 is 36, if I don't think about that, I can just work directly with 73 over 37 and use quadratic reciprocity. Let's do this just to see that we get exactly the same answer, no matter how we do it. And it's up to us to choose whatever properties we want. But what I'm saying is that this list is complete and will always solve the problem, no matter what number I have to compute, what quadratic symbol, for the following reason. I look at the number that I see, 73 mod 37, but 73 or another number. Is this a prime number or not? If it's a prime number, then both are primes, I can use quadratic reciprocity. If it's not a prime, at least I can write as a product of smaller numbers. So I reduce the problem all the time to computing smaller numbers. Until I get to 2 over p or minus 1 over p. And then I'm done, because I apply directly. So let's do this in this particular case and see what we get. 73. Now let's see. Is this equal to (37 over 73), the Legandre symbol, or do we need to put a minus in front? Well, I just look at the quadratic reciprocity. It says I have a minus in front of it exactly when I'm in a situation where both primes, P and Q, are congruent to 3 modulo 4. So I look at my numbers. Is it true that both numbers, 37 and 73, both of them are congruent to 3 mod 4? No, 37 is congruent to 1 mod 4. It's enough, I don't need to care about 73. But 73 is also congruent to 1 mod 4 in this case. But once I have one number that's congruent to 1 mod 4, I know I have a plus in front. It doesn't mean that the symbol is plus 1. It's just that these two are related by this equals that. No minus in front. If I write this for, say, on an exam or whatever, in any other circumstances when I think that someone will read this, I want to explain what I'm doing very quickly. I just say by quadratic reciprocity. It's plus 1 quadratic. And when I say by quadratic reciprocity, I want to show that I know what the quadratic reciprocity states. I need to show that this is plus 1 in front because at least one of them is congruent to 1 mod 4. So I just write this. Somewhere I add this without any other explanation. 37 being congruent to 1 mod 4. Add this explanation there. So the fact that 37 is congruent to 1 mod 4 and using quadratic reciprocity gives me that relation. There's no more space there, so I will do the following. For those who follow the video, maybe they want to write down on a piece of paper these properties, stop the video, write down the properties, so I can erase the board.
They can rewind as well.
So we can continue solving this problem. We have enough space. Actually, we use these properties a couple of times and we will remember them. So I'm left with 37 now over 73. Now what? I don't know what to do. Again, I have to. If I use quadratic reciprocity, I go back to where I started. So maybe I need to do something else. I don't know. Write that this is equal to another one, another symbol when 37 is replaced by a number that's congruent to 37. Maybe say if I subtract 73 from 37, I get actually minus 36. Now we can use our multiplicativity property of this quadratic symbol and write it as I see this, or I view this minus 36 as the product of two numbers, minus 1 and the other one is 36. So then I can write this as, thank you, minus 1 over 73 times 36 over 73. Then I start computing each one separately. This one is directly 1 because I have a square. And this one, let's compute here. It's minus 1 over 73. Oh, for this I have a formula because I have a minus 1. Minus 1 to the, it was 73 minus 1 over 2. P minus 1 over 2. So this minus 1 to the 73 minus 1 is 72, divided by 2 is 36. And this is plus 1. Now that I have this plus 1, I can come back here and I know that this is the plus 1. So I can come back to this and conclude that the product is 1 times 1 is 1. And if we combine with what we had before, it gives us the 73 over 37, the initial number that when we computed is 1. So in conclusion, we did it in two different ways. Let's say conclusion. (73, 37) is 1, which means 73 is a quadratic residue. So that's our answer. It's a quadratic residue mod 37. I think we'll need to see another example. I don't know if we do it now or in another or in the next video.
We can do
it's
it
too
now.
long.
We can do it now.
All right. Let's see. Maybe it was
10 more minutes.
10 more minutes. Let's do one on the exam. As I said, it starts like this.
Similar.
Similar. Is the congruence x squared congruent to 11 mod something? Some large number. Solvable. Exactly. Here's the congruence. X squared congruent to 11 modulo something. I need another prime number. Let's say a 2-digit prime number.
23.
23. Good.
Larger.
Stop. Solvable. Question. Again, we compute the symbol and see if it's +1 or -1. And we say, compute the symbol, 11 over 23, quadratic symbol. I can use the quadratic reciprocity again, because this is a prime, and write it as 23 over 11 with plus or minus in front. I check the two numbers. Let's see if they are congruent to 1 mod 4, 3 mod 4, or whatever. Now 23 is congruent to 3 mod 4. 11 is congruent to 3 mod 4. So we are in a situation where both of them are congruent to 3 mod 4. So I write, so then I have a minus in front. And I give a quick explanation here. We used quadratic reciprocity. In combination with the fact that both numbers are congruent to 3 mod 4. So I write under this 11 congruent to 3 mod 4 and 23 is congruent to 3 mod 4. Good. So I add this explanation right here. Now, I have minus 23 over 11. I cannot take the minus in front or take it out or whatever. No. I have this minus. I keep track of this. Now, 23 over 11. If the number in the numerator, so to speak, or as I said, the number of times, it's not a fraction. It's larger than the one that I have in the denominator. I can replace it by something smaller, because I can add and or subtract any multiple of 11. And in this case, if we subtract 2 times 11, I get 1. Of course, I still have the minus, because it's minus times the symbol, but this symbol is 1 over 11. Because, again, 23 is congruent to 1 mod 11, so the two symbols are the same. I have a minus in front. Now, 1 is a square. 1 over 11 is always 1. 1 over p. The quadratic symbol is always 1 for all primes p. And I still have this minus in front, so I have a minus 1. Now, let's see what was this. Oh, yes. This was the actual symbol we wanted to compute from the beginning. And it's minus 1, so we can give the answer to the problem. Answer. And now. Answer. Let's see what the question was. Is this quadratic residue or non-residue? No, it was about congruences. Is the congruence solvable? And the answer, I got the minus 1 here. No. Answer, no. Congruence. What congruence I'm talking about? This one. X squared congruent to 11 mod 23 is, it's not solvable. So, in conclusion of this video, if I have to compute a quadratic symbol, I use those properties. And I do want to compute a quadratic symbol if the question is, is a congruence solvable? X squared congruent to something, modulo a prime number solvable? Or if the question is this number 11 a quadratic residue or a quadratic non-residue? In both cases, I compute the symbol. How to compute the symbol? If I have a number at some point that's larger in the numerator than in the denominator, I can subtract multiples of the one in the denominator. I'm getting smaller numbers. Or if the number in here is a product of two numbers, I use multiplicativity. I can write it as a product of two symbols, as we did before. It was -1 times 36. Or if the number is a prime there, I can use quadratic reciprocity and change the product. So by combining these steps, sooner or later we get to smaller and smaller numbers, and we are able to compute the symbol. All right, I think we can stop this.